Now we will look at how to define a network. So basically, PyTorch offers a way to easily declare networks. So getting to define explicitly all tensors directly would be a difficult task. We don't want to do this in most cases. So we have the package torch.nn that inherit from nn.module that allow us to define some kind of network. We could just define our class. So here we need to rely on some, hope most of you know what is object-oriented programming, or at least as some basis on object-oriented programming. The idea is that we define a class. A class in object-oriented programming is like a concept, a structure that contains some functions and some variables inside. And so this class, we define it with the init function that will be called when we will construct the network. So we just call super.init as in the way we do this in Python to be sure that the constructor of the parent class and then module is called. And then we can define the layers, the nonlinear operations, the regularization. So everything in there can be stated, can be provided within the init function. And then in the forward function, we want to make difference there. We want to implement how things are processed from the input to the output. So we define our network that way, so we can implement different topologies directly there with defining the constructor and the forward function, right? There are several types of layers that are available in PyTorch. We are usually composing simple modules together to build up more complex modules. So for example of basic modules include linear module, torch.nn non-linear, where we have a number of input features, output features, and we have a bias or not, it depends. We also have 2D convolutions that allow us to apply this with different configuration, different kernel size, stride padding, whatever. These are different parameters to describe how our convolution is done. We also have dropout. We can implement dropout directly on the different layers with some parameters here. You can look at this at the NN module documentation for more details on that. So most of the layers are also available as functions from torch.nn functional. However, this module, when we are calling them, we are not registering them. So as they are called as functions. So basically, and these parameters are not taken into account in the list of parameters. And even some layers like dropout and batch norm have different behavior in training and testing. So if we change our network mode, the function layers will not necessarily be changed. We need to manage that. So in general, it's better to use function layers only when there is no parameters to optimize. For example, if you have an activation function, a ReLU function, we don't need to define this as a full layer. We can use this, define this as a function layer. That will be well enough because ReLU, there's no parameters to learn, no backprop to be done, nothing in that. Is just a basic function that is transforming the input into something else. Let's now assume the LNet5 network that we have here, which is really basic convolution neural network, classical one from the 90s. The implementation of LNet5 in PyTorch looks like this. So we have a class which we call LNet5, where the constructor is building up the network by setting up the different layers. So we have the convolution layers as C1, max pool as C2, S2, convolution, max pool, linear. So basically that's the kind of setup we can get: 2 layers of convolution, 2 layers of max pooling, 3 layers of fully connected linear models. And when we do the forward, it's not just about so we have this structure here, but we go by adding also the ReLU. So we are connecting C1 on S2, but having a ReLU in between, likewise for SC3 to S4. Then we can resize it, the right thing, to kind of put the output of the different convolution as a flat, more standard, let's say, tensor. And then we apply ReLU on the output of C5, and which is taking the Y as input. And then we also apply again F5, F6, sorry. and then again with ReLU, and then we have the output. So it's the flow forward in terms of having the different, the flow of the information in the two first convolutions, and then the remaining layers of the neural network. Then if we want to do the training on the GPU, it's kind of simple. We need to build up the model and move it on the CUDA, so move it to the GPU for execution on the GPU, and then we can move it back to the CPU and process it, analyze it, the results. So it is possible also to change the network mode, so it will change the behaviors of layers. Somehow, if when we are training, the way we process data is different than when we are testing. So if we see that train, we put the network as in the training mode. If we see that eval, we put it into the test evaluation mode.